We'll start the session in another 5 minutes. Operating system. So operating system actually it is a main program which is working on a computer computer. Whenever you plug in your keyboard, whenever you want to display something on your screen, or if you want to manage your files in the directories on your system. So basically, the program which keeps on running, which does all these tasks, is the operating system. So in case of larger systems, the operating system requires the operating system does much more jobs, like it looks for the security of the system, and if multiple programs are running and multiple users are running programs, so operating system mainly takes care of these activities and does not create any conflict. So as we go through the slides, in the main slide, first slide, you see the operating system is a master control program. Some colleges are unable to hear me. No audio clarity. Just a moment. Okay. So here, as you see, the operating system is the main master control program. It manages all the software and the hardware resources. So operating system mainly controls, allocates, frees, and modifies the memory by increasing or decreasing it. So the main role of through our slides later, we can see the detailed use of the operating system. So operating system are generally categorized into three categories. One is a general purpose operating system. Other is operating system. And third one is real-time operating. So in a general purpose operating, it's a normal operating system which mainly does all the services. Like for example, we have a Windows operating system and Linux operating system, and DOS, or all these are general purpose operating system. And we have embedded operating systems like VxWorks, example. And we have a real-time operating system. Real-time operating system means here the service has to be very deterministic. It should be in a defined time. The number of services are less. Services has to be deterministic. It should be of real time. So that's a real time operating system. So these are the three different operating systems which are types of operating systems which are available. So I think I didn't give the description for the embedded operating system. Embedded operating system also has a very limited number of services, but they are not very critical or time bound. Limited services available in the embedded operating system. So operating system. Again, I repeat, system is a software. It's a software platform on which all the user applications run. As we go to the next slide, so I described before, it also manages files, disks, and security, and provides device drivers. We will discuss about it later, and the graphical user interfaces, desktop or mobile computer, and the other functions and the applications. It enables the assignment of priorities for requests to the system and controls I/O devices and the network. It assigns, basically what it is trying to say is that it enables the assignment of priorities for whatever process are there in your system. And it also controls all the I/O devices and the network. As we move on to the next slide, here we see a device driver. So a device driver, it's a software component which enables the use of a device. Like, for example, a device driver, it lies on the top of the hardware, on your hardware, to make it function effectively. If you plug in your USB, a device driver will be run to know that a USB has been detected. So this is a software program which directly interacts with the hardware. And we have on top of hardware, device driver, and on top of that kernel, and on top of that we have applications, user applications running. So the main functionality of the device drivers is like it enables the use of the device port or network by configuring open, close, connect, or specifying a buffer size. All this configuration will be pressed on the device driver and sends output or receives the input of the hardware. So driver functions, you can see create, delete, open, close, read, write, I/O control, connect, bind, listen, and accept are some of the device drivers functions. The other functionality of the operating system, it has utility programs. For example, file manager in the configuration of the OS. It also does the file management basically. And we have in operating system, the main part which interacts with the hardware is the kernel. The kernel is mainly responsible for process management, access control, memory management, and I/O file system, and all the device drivers. So kernel is the heart of the operating system in the case of Linux. In the case of Windows, here he is telling like in the second line can be accompanied by a specific suite of applications, for example, Internet Explorer and the MS Office. Now, is in the operating system, when you run your program or an application, it comes up as a process. So process is really a program in execution. So the process will be scheduled by our operating system, and it has to go through different states. And once the task is done, the process is closed. So the process can call a function but cannot call another process directly. That is all done by the operating system. And we find a different states for the process. So first we create a process. In case of Linux, we can use a fork system call to create a process, child process, and the process can be in an active state. But the process is running in your operating system, it will be in the running state. And if some other process interrupts this current process which is being executed, the process can go into the suspended state, and fifth state is pending for a specified time interval. So these are the different states of process which are available in the operating system. So in this slide, we see pending state of a process from other process. In this side, we see different mechanisms for inter-process communication. So we have semaphore, signal, mailbox message, queue message, and a socket. Detailed explanation will be provided later. So in our operating system, every process is treated as a task. A task structure is maintained in the operating system for a process. So an application process which runs according to its schedule set by the OS. An application process which runs according to it's an application process which runs according to its schedule set by the OS. Each state of is controlled by the operating system. So the task state, it means that the task state is controlled by the operating system. And the task can be a real-time task which has a time constraints or maximum defined latency within which it must run or finish. This is basically telling what are the different kinds of tasks which are available. Thread. So thread is a part of a process. You can say like for a process, we have a process control block which maintains all the data, and threads, like a process can have multiple threads running. Like a process into several threads and it can be executed fastly. So threads share the same memory allocated for the process. So in a process, we have the memory divided into different regions. Text segment, we have a text segment, heap segment, stack segment present for a process memory stack. So thread also shares the same stack of the process. So why do we require threads is that the context switching is very easy and the OS can perform its tasks fastly. That is why a process are divided into threads. So operating system, we can have a multi-user operating system, multi-processor operating system, multitasking operating system, and real-time operating system. Multi-user operating system, multiple users can run their programs concurrently. Multitasking operating system is several tasks run at the same time. Multi-processor operating system, like a process can run on different CPU. And the real-time operating system is like the tasks are of a classified of real time. So here we get different types of variants of operating systems based on the threading and the process. So thread, as we go in the next slide, thread is a lightweight process. Lightweight, it does not depend on certain system resources. For example, memory management unit does not depend on certain system resources. For example, memory management unit, GUI functions provided by the operating system or the functions which need running of other processes or threads for their implementation. Next comes the interrupt service routine. Like whenever you are typing a key on your keyboard, so it generates an electrical signals to the processor and it goes to the interrupt controller. The interrupt controller is a program which is running in the OS, which it informs that a key has been pressed and it sends the signal to the processor. The processor might stop the current process which it is executing and serve this interrupt using the interrupt IRQ. So interrupt request IRQ. So the interrupt controller maintains the function which has to be invoked for the particular key which is pressed on your keyboard. These electrical signals go into the interrupt controller pins and they are converted into a code. So based on the code, a corresponding interrupt function will be invoked. This is the job of the interrupt controller to invoke a proper functionality. So in case of Linux, if the kernel is performing the task of the user space application, it is called as a process context. When the processor is executing any interrupt, it is said to be working in a interrupt context. So in the interrupt service routine, a program unit, function, method or subroutine which runs is a program unit which runs when a hardware or software event occurs. So running of which can be masked and can be prioritized by assigning a priority. Higher priority than any other process or tasks or the threads. So interrupt has the highest priority than any other process or threads. Interrupts are generally given a higher priority in the operating system. Hardware events for interrupts. Like a timeout of a timer, clock tick timer is one of the hardware event of the interrupt. And division by 0 can raise one interrupt. And overflow conditions can raise one more interrupt. Underflow detection by hardware during the computation can also raise an interrupt. So these are the different ways we can raise a hardware event for an interrupt. These are also some examples of the hardware events for interrupts, like finishing of the DMA, direct access. So DMA means like for example, DMA is like for transferring the content of content of memory from one location to another location without involving the CPU cycles. Like we have a DMA controller, and our operating system will give will configure the DMA controller that you have to take this portion of memory into this location. It will give a DMA request, and the DMA controller has its own managers quickly move the piece or chunk of memory from this region to another region. Like for example, real-time example, like when you're receiving the packets from the network, we have a Ethernet controller chip, which mainly data from the network and copy it into your CPU RAM memory. So in such cases, they configure the DMA and move the data quickly. So the first sentence means like finishing of the DMA. Once the DMA transfer has been completed, then an interrupt request can be raised to the CPU that your DMA transfer has been done. This is one example of the hardware event. And data abortion. Like you can stop transferring of the data on certain cases. An external FIQ, fast interrupt request through a pin input. External IRQ, interrupt request through a pin output. And a memory buffer becoming. These are the various hardware events for the interrupts. We go to the next slide. Hardware events for the interrupts like for port, transmitter, receiver, or a device buffer becoming half filled, and the buffer with at least one memory address filled, the buffer becoming empty. These are all the different scenarios in which hardware events can be raised. So he's listing out each and everything here in the slide. Buffer associated with the memory address for the LCD, printer, serial or USB port, keypad, or a. So now the software related event section. Software instruction when you are executing your program. So in between an instruction in the program can raise a software event. Software instruction. So software instruction for interrupt on detection of certain condition during the computation or error while or handling on some error conditions in executing of your program. And it can an illegal operation code provided to the CPU. So these are the software interrupts which can be raised. So similarly, we have interrupt service thread. So when you so this is the the previous slides indicated these are the different scenarios of where hardware and software interrupt can raise. In a Linux operating system, if your application wants to interact with your hardware, we need generally you must have executed your C program. You will generate an executable. So if your program wants to interact with some part of your hardware, so like for example, you are using printf or scanf statements. So the printf statements internally use a C library, and in C library, the printf has the implementation of its system call, which tries to interact with the kernel using the sys write command. And this command, this goes to the kernel. Kernel directly interacts with your keyboard screen. It's your monitor, and tries to give the text which you have given as an input in the printf statements. So in the printf statement internally calls a software interrupt. Interrupt number is 0x80. So every system call has a entry in the system call table. So through that table, it tries to invoke a routine and invoke the corresponding system call routine, and it does the task effectively. So the core of the operating system is a kernel in the case of Linux. So I concentrate much on the Linux because system, and we take reference of that for the various implementations in our mobile operating system. I hope you will be clear now on what is a process and the thread and what are the steps. So as we move, we also go to various other operating systems. Like in mobile, we use an operating system called Android operating system, which is built on top of the Linux. On Windows, we have Symbian OS. So my next team member will continue on what are the various operating systems available on the mobile. So one such is the Windows CE, one which is Windows CE operating system. So Windows CE operating system is that. So here he is talking about CE IST. That is one which is here all the ISTs are placed in the priority queue so that ISTs execute turn by turn. Event, and the ISR puts a message or a semaphore or a signal for the IST. So I said like okay. We'll discuss about the interprocess communication later. Signals and semaphores, all these things come under the interprocess communication. So, detail will be explained later. So, as of now, just remember an IST is initiated and put in the first in, first out queue according to the ISR priority. And after the execution of an ISR starts on an event, the ISR puts a message or a semaphore or signal for the IST. So with reference to this, so ISR is an interrupt service routine and IST is an interrupt service task. We take in the case of Linux, we have top halves and bottom halves. Interrupt service routine, like the mission critical task which has to be executed on the code is executed in the top half, and the task which can be executed at the later point of time is treated in the bottom half of the code. So you can like that. The ISR therefore has an event initiated piece of code which runs on the critical part of the code, and the rest of the code runs at the IST initiated by it. So IST can be treated as a bottom half, and ISR can be treated as a top half. The IST priority lower than the ISR, but higher than the process or the task or the threads. Okay. So the next part is the page. Page is generally it is a part of the memory management in your operating system. So whenever your system boots up, it comes up in two modes. One is a real mode. In real mode, when your system comes up, all the memory is seen as a flat, a set of arrays. But when it comes in the protected mode, the memory is treated as a frames, and on top of that, so on top of that, it is treated as comes up. Your process completely comes up. There is a memory management unit which is coming into picture, which divides your memory into frames and pages. And then whatever pages which are maintained in your operating system is generally has its entry in the page table. The memory management unit takes care of this, and the memory management unit is again controlled by the kernel. So for any process, example, like whatever RAM is available on your system, so it's a kernel which takes this much amount of. Suppose you have a 4 GB RAM, so you can see like for your process, a 4 GB of memory is allocated. Virtual address space. Generally, virtual address space will be allocated. So once your system comes up, so it's a process can see only a virtual address space. But in the real mode, like when it is trying to come up in the beginning, it is only seen as a set of arrays. So what we bother is like what will happen when the system completely comes up. At a time, we always see that at a time, we see that only the complete a single process is running on your CPU. But in fact, it's the kernel which of executing multiple processes at the same time. So, memory is allocated to a process in the form of pages. So a page is a unit which can load from a program stored in a hard drive or from any other storage device to the program memory RAM before the execution of the program. So it's a contiguous memory address block of 4 kilobytes or 2 kilobytes or 1 kilobyte, depending upon the 32-bit or 6-bit operating system. It tries to allocate the pages. So page table is used for the address mapping. It provides a mapping of the fragmented physical memory pages with the pages of virtual addresses, which are memory addresses. So what is fragmentation? So it's a question for you to explore. I hope most of the people are aware of it. Just take it as an exercise. So pages of a memory are spread over the memory address space, leading to the fragmentation of codes and data in the physical memory space. The pages of memory are spread over the memory address space, leading to the fragmentation of codes and data in physical memory space. It's all your memory can be allocated and deallocated, and it might leave fragments in your memory region, and it is the memory management unit which takes care of taking all the fragments and allocating memory for you for the future programs. It all does this with the help of page tables. So it's a memory management unit, creates and maintains the page tables and hence performs address mapping and translation. So the linear to physical, physical to virtual addresses mapping, everything is done by the memory management unit. So when I talk about the virtual addressing means that like even though you have amount of memory, 4 GB of memory is available. So it's a memory management unit which gives a feel like, okay, you have a lot of memory for your programs. So when your program is running, it is the process feels like, okay, yeah, it is having all the memory is used for being used for it, allocated for it. But in fact, it's not. It's a memory management unit which has which performs the scheduling, time slicing, and all this stuff with the help of the kernel and executes the task. So, so process feels like it is being addressing the whole memory using the virtual address mechanism through MMU. So program during the execution first. So in the second line, program during execution first translates the accessed address as a virtual address into the physical address using the page table at the MMU, and then access the physical address and fetches the code or the data. It's the actual operation which is taking. So MMU when program during the execution first translates the access address, virtual address into a physical address using the page table at the MMU, and then access the physical address and fetches the code or the data. Priority inversion. Priority inversion, this is a concept means like, so suppose when a process or thread is being executed, then when a middle is being executed, when another process comes in between, like with a of less priority, tries to interrupt the current running thread which has a higher priority. So then what happens is the processor tries to allocate the middle priority process or the thread write memory for it and try to execute this. What happens is a priority inversion. That means the low priority is given importance and the high priority thread and being executed. So this is called as a priority inversion. So once the middle priority thread finishes its task, then it will leave the resources for the higher priority process and then it will continue its execution. And priority inheritance is like whatever, so suppose thread is a subject of, you can say it's a process. So whatever priority your process has, when a thread is created from a process, it also inherits the same priority. Waiting object, it's like signal, semaphore, queue, mailbox, or bytes from the pipe. So pipe, what is a pipe? So this is one of the mechanism in the IPC, and it is the category of communication. So pipe is generally like one end you can read the one end you can insert the data, you can write the data, and the other end you can read the data. So pipe is a virtual device which sends the bytes from a thread, from one thread to another thread. So like pipe, we have a named pipe called FIFO. So okay, so as we have come to the pipes, we will also see other mechanisms of the interprocess communication. So we have, as I said, in inter-process communication, when one process wants to communicate with another process, then we use the inter-process communication mechanisms. So under this, we can categorize the inter-process communications into three categories. One for communication, another is a synchronization, and the third is a signaling. So under communication, we have two types of communication, either data transfer or the shared memory. So in the case of data transfer, we have two types again, classified into two types, transfer and the other is a message transfer. So under byte transfer, these mechanisms like pipes, FIFOs and the stream sockets come into picture. And when it comes up the message transfers, we use message queues and the datagram sockets. When it comes to the shared memory of part of communication, we have system-wise shared memory communications and POSIX shared memory. We also have under shared memory a memory mapping mechanism for anonymous memory mapping and the file mapping. So then, so in communication, we have, again I repeat, we have two categories, data transfer and the shared memory. Maybe I can write it and use a whiteboard. So under communication, we have two categories. One is data transfer and another is shared memory. So in data transfer, it is again classified into byte transfer, message transfer. Under byte transfer, we have implementation of pipe before named pipes and stream sockets. And in the message transfer, we have message queues. Message queues, datagram sockets. In shared memory, we have three categories. System 5, shared memory. POSIX shared memory. And memory mapping mechanism. So in this memory mapping mechanisms, you can have anonymous memory mapping and file mapping. You can note it down somewhere. So in interprocess communication, one category is a communication under which we have a data transfer and the shared memory. Data transfer in the shared memory. Under data transfer, it is classified into another two types: byte transfer and a message transfer. Where byte transfer means it transfers in the form of bytes using mechanisms like pipe, FIFO, and the stream sockets. In the case of messages, message transfer means like a buffer, buffer or a message, it is transferred. So it is done using message queues and datagram sockets. And the case of data transfer. So in data transfer, the kernel will be involved for moving the data from one part of memory moving the data transfer from one part of memory for one process to another process. So in the case of shared memory, the process can share a portion of memory without involving the kernel. So for that purpose, we use system file shared memory, POSIX shared memory mapping mechanisms. So similar like this communication category, we also have a category called synchronization. So you can go to the new white page. Synchronization mechanisms are semaphores, so why do we require synchronization mechanism is that so when a critical portion of code or memory is accessed by different processes, so there should not be any conflicts while allocating the memory for it for this portion for this conflicting process. So for that purpose, we use a synchronization mechanisms. So several synchronization mechanisms like semaphore synchronization mechanisms are used in our operating system, Linux operating system. Semaphores can be used within the process as well as threads, but whereas in mutex can be used thread related operations. Under the file log, we have two more categories: file log and record log. In semaphores, you have system semaphores and POSIX semaphores. System 5, POSIX. The type of synchronization mechanism is thread related. So in thread related, we have four categories again, divided into four types. Text, condition variables, read red logs. So these are the various communication synchronization mechanisms available in interprocess communication. Hope you had a note of all these things. And the third kind of mechanism is signaling. Signal like suppose like floating pointer exception, or if you are trying to access some illegal memory. So we, in your common example of C program, we have while executing a C program, you might be coming across a orientation fault. So all this comes under like sig segue, sig kill, sig stop. All these come under this signaling mechanisms of interprocess communication. And the sockets, suppose might be when you are trying to communicate in your internet, we have something called as a client and server. So there we use the interprocess communication for the networks like client socket, server socket. That is for the process communication over the networks. So example of the Linux operating system here we use is the, so we done with interprocess communication. Now we go to the operating system. So one of the common example of our Linux operating system which we use on our mobiles is Office. So why did we go for the Linux operating system? It's an open source operating system. It enables the users to customize their device to suit their specific needs, and it provides the ease to different sorts of hardware and software applications. Daily customization is possible. Linux is an open source. So Android is built on top of the Linux. Design user interface, managing the power consumption in devices, and the real-time operation. It is also considered to be more secure than most other operating systems, and several international mobile phone manufacturers use Linux for their OS requirements. So here it's taken an example of Motorola Rocker E2 music phone. It's a Linux-based mobile phone with a 240 into 320 TFT display with 262,000 colors, and it is provided with USB 2.0 for fast drag and drop data transfer, built-in FM radio, support for Motorola's iRadio service, support for Bluetooth. So it's taking an example of a phone which is supporting all this. So basically we have an operating system. It's a software platform which is provided on top of which applications are written. So an operating system takes care of your hardware, provides a platform for the applications to interact with the hardware, and it also does the memory management and all this kind of stuff. So basically it's a master control program. It manages all software and hardware resources. It controls in allocating, freeing, and modifying the memory by increasing or decreasing it. And it controls all these processes, tasks, threads, interrupt service routines. It also manages the files, disks, and the security, and provides device drivers and also the graphical user interfaces for your desktop or the mobile computer. It also has memory management to take care of handling of the memory related operations. It also does priority inversion as well as inheritance. And one of the operating system, much famous operating system which we use is the Linux operating system, on top of which our famous mobile Android operating system is built. And it enables the users to customize the devices to suit their reviewing all the previous parts. One more PPT related to the mobile operating system. We can have a quick look on the PPT also. As I have already told in the previous when we are going to the previous slides, we have a general purpose operating system where it provides more number of services. So Linux is one such operating system, like general purpose operating system. Um, so it can be implemented on the machines which with a different like on your laptops or PCs you can load your Linux operating system. But when it comes to the mobile, we have a limited hardware available, like a small screen available, and we have an on-screen keyboard, different graphical user interface, different video interfaces. So we have your smartphones and tablets. Everything comes with a different configuration. So we need to customize our OS to be compatible to our mobile devices. So it can run only a limited number of services. Can be classified as one of the embedded operating system. So when you suppose you might be using your Samsung or different other phones, it might be use a Qualcomm chipset or Snapdragon boards and everything. So on top of that, so on top of Linux, the Linux operating system has to be customized with the Android operating system loaded on top of it. So on your phone, you have different apps available. So like on your, if you compare with your Linux operating system, if you have a shell interface, you open a terminal. So it's a shell application, shell service which is available. So you can also parallelly run another on your Linux operating system. Like when you take in comparison of the different apps, so it comes as a .apk files. So to these APK files will be understood only by the Android system. If you have your Ubuntu laptop, so the Linux operating system is customized to your desktop, like a desktop interface. So these are the different variants of the operating system which are available on top of Linux. So Android is based on Linux, but it is not completely Linux. It is customized for our. So like Android, we have also Symbian OS, Palm OS. That the detailed architecture of that operating systems will be taken by my colleague in Thursday session. So now just go to the quickly slides of what this mobile operating systems contain. So mobile computing system, we have a specialized hardware, graphical user interface, video user interface, and it has a provision for the mobile communication. Like mobile you need to place the calls. So we have some modem application running on your operating system to achieve this activity. There are many constraints, for example, the constraints of connectivity, CPU speed, memory, battery life, display, and the size of the input devices. So it's very limited. So we should make use of these limited resources to achieve our activity on mobiles. So a mobile operating system is an operating system which enables running of application tasks taking into account such constraints of hardware and network. Excuse me. It enables a programmer to develop an application without considering the specifications of the drivers and the functionalities of the hardware of the system. So, end user can write his own app without actually worrying about what kind of hardware it is being deployed. It has to be deployed. So mobile operating system provides us the convenience to write our own app as a driver, which is a software component which enables the use of the device, port, or by configure it properly and sends outputs or receives the input. So mobile operating system enables an application to run by simply abstracting the mobile system hardware. It enables the programmer to abstract the devices such that the applications need not know the full details of the font and the font size of the mobile device display, and the application need not know how the message will be displayed by the LCD hardware. The developer writes the application and the mobile operating system which takes care on what device it has to be displayed. The examples of the mobile operating systems are system, Windows CE operating system, Symbian, and the latest one is the Android, where everybody is aware of this. Example of hardware abstraction by the operating system. Keypad, LCD, display, serial output devices are abstracted by an application as the input and output devices with the device numbers 1, 2, 3, and 4 respectively. Okay, here he is giving an example of hardware abstraction by the operating system. A simple example, maybe just go quickly. So what is he saying is that keypad is given number 1, LCD display is given the number 2, serial input is given number 3, and serial output devices are given number 4 respectively. Now what he is doing, write 1, that is keyboard, welcome to ABC Telecom, when a message welcome is sent in the output for display. So from the keyboard we are writing onto the 1. It seems this write instruction has to write it onto the display device. So, so it is a duty of the operating system to associate the corresponding, takes the entry from the keyboard and could write it onto the any display. So it provides the abstraction to the user. So mobile OS facilitates execution of software complexified mobile device hardware. Application need not be aware of the details of the LCD driver and the memory at which the CPU will send the message for the display. So he say telling the same point again and again, reiterating. So like normal operating system, mobile operating system also provides interfaces for communication between the processors, threads, and the interrupt service routines at the application and the middleware layers. So provides the middleware for the system hardware. And like in our Linux operating system, how we have a kernel, this also provides a middleware for the system hardware. And it also provides management functions such as creation, activation, deletion, suspension, and delay for the tasks. It also provides the memory management. It also enables running of the processes. It helps the processors in obtaining access to the system resources like our normal operating system. And in application tasks, it has some application tasks. The operating system provides the functions used for scheduling the multiple tasks in the system and synchronization of the tasks by using the semaphores. And the task can have multiple threads. Task is nothing but a process, and the process can have multiple threads. So it is called as a multi-threaded program. And in mobile operating system, it provides for synchronization of the threads and their priority allocation, and it accomplishes real-time execution of the application tasks and threads also. And the application uses the system resources, for example, the CPU, memory, keypad unit, modem interfaces, USB or serial port, and a battery. So resources shared concurrently by all the applications which are running on the system by the OS. And the user applications like graphical user interfaces, voice user interfaces, I'm sorry, it's not a video, it's a voice user interface components, and phone API. Mobile OS provides configurable libraries for the GUI in the device and provides for multi-channel and the multimodal user interfaces. So on summarizing it, mobile operating system is an operating system which enables running of the application tasks taking into account file system constraints of the hardware and towards the network. It enables a programmer to develop the application without considering the specifications, drivers, and the functionalities of the hardware of the system. It has its device drivers, GUIs, voice user interfaces, and the phone APIs. And that's about our mobile operating system. So in Thursday's session, we'll go in detail about the Palm OS, Symbian OS, and the Windows CE, which will be covered by my coach Jitendra in the next sessions. Thank you very much. If you have any queries, please get back to me.